Okay, so welcome back everyone. This is section 2 determinants, and this is part 2 of the videos. In part 1 we learned how to find a determinant. In part 2 we'll take a look at what one would use a determinant for. Specifically, we're going to take a look at something called Cramer's rule. And Cramer's rule is a technique where we use determinants to solve a system of equations. So by definitions, Cramer rule is an explicit formula for a solution for a system of linear equations when we have as many equations as we have unknowns. Okay? It also only works when the system has a unique solution, meaning the no solution or the infinite solution problems won't work this way. It's kind of like matrix algebra in that sense. Okay? Cramer's rule expresses the solution in terms of determinants. So basically what you do is you write the answer by finding values of determinants and reducing fractions, essentially. The definition or the rule for Cramer's, I guess I don't know how you'd say that better, is you make determinants using the coefficient matrix and replacing columns in the coefficient matrix with the constant matrix, that column matrix from the right-hand side of the equations. So let's take a look at an example and see if we can make more sense out of this ugly definition. Suppose we had a system of equations that when written as a matrix system look like this. So you have a matrix A, B, C, D over there on the left, and that matrix A, B, C, D over here, these are the coefficients of your variables x and y for your equations. And then we have the matrix EF, that column matrix over there on the right, which are the constants that the system is set equal to. So this would be something like the system 2x plus y equals 4, and how about 3x minus 4y equals negative 5. So that would give us the coefficient matrix 2, 1, 3, negative 4 times the variable matrix x, y is equal to that column matrix 4, negative 5, which is our constants over there on that right-hand side. So that's those guys. Okay. Now, according to Cramer's rule, the solution to this system is just found by finding the determinant of this matrix divided by that determinant of that matrix, and y is found by this one divided by that one. So did you see what happened in these? The denominators of both of these are just the determinant of the coefficients. The numerators are that coefficient matrix with the, in this case, the x variables replaced with the constants, and in the second one, the y variables replaced with the constants. So then for our example over here, we would get that x is equal to the determinant of 4, 1, negative 5, negative 4 over the determinant of 2, 1, 3, negative 4. And our y would be the determinant of 2, 4, 3, negative 5 over 2, 1, 3, negative 4. And then we would calculate those determinants and then find the values. Right? So I'm going to calculate the determinant of the numerator. I have 4 times, remember, determinant of a 2 by 2. You do that loopy-doop thing, right? Boom, boom, yeah. And so my numerator is going to be 4 times negative 4, so it's going to be negative 16 plus 5 over, downstairs I've got negative 8 minus 3. Negative 16 plus 5 is negative 11. Negative 8 minus 3 is negative 11. Negative 11 divided by negative 11 is 1. Okay. Down here I know the bottom is going to be negative 11 because this is the same as this. So my numerator will be 2 times negative 5, so it's going to be negative 10 minus 12. Negative 10 minus 12 is negative 22, so negative 22 divided by negative 11 is 2. So then x is 1 and y is 2, and I'm done. And this is called Cramer's rule. Does it work for 3 by 3 systems? You bet it does. Oh man, I know you're so excited, and so am I. You just do the same kind of thing. Okay? So you replace for x with the constants, replace for y with the constants, replace for z with the constants, find those determinants and make it happen. All right? So let's just do an example down here and then we'll call it good. All right, so here's my system. My matrix equation would be 2, 5, 2, 8, x, y, 15, 18. So then x is going to be, and for x, I'm going to replace the x with the constants. And so it is going to be the determinant of 15, 5, oops, not 8, 18, 8, over 2, 5, 2, 8. Okay. And then y, I'm going to replace the y with the constants. So y will be the determinant of 2, 15, 2, 18 over 2, 5, 2, 8. And then let's go back and calculate those things. Let's see, upstairs I have 15 times 8. Remember, I'll say it again, but remember for a 2 by 2, we do this loopy-loop thing, right? And so I've got 15 times 8 minus 5 times 18. So I've got 30 upstairs. Oops, I don't want that. That erases. I've got 30 upstairs, and downstairs I have 2 times 8 and 5 times 2. 2 times 8 is 16 minus 10 would be 6, and so I get that x is 5. And then I'll do the same thing over here for y. Okay. I know the denominator is going to be 6 because this is the same as that. I just got to figure out the upstairs. I have 2 times 18 minus 15 times 2. Bing. That gives me 6. 6 over 6 is 1, so that means that y is equal to 1. And so then the solution for my system is 5, 1. X is 5, y is 1. And if I wanted to, I could check my work. 2 times 5 is 10, 5 times 1 is 5, that adds up to 15. 2 times 5 is 10, 8 times 1 is 8, that adds up to 18. It does work. Okay. Now, Kramer's rule is a technique for finding solutions for a system using determinants. Nothing more, nothing less. So at this point, you now have, what, 4 different techniques that you can use to find solutions. You could do row reduction by hand. You could do that Gauss-Jordan on the calculator. You could do matrix algebra. Or you could use Kramer's rule. Which way is the right way to do it? There's no answer to that question. You just know that there are many ways to do this. Which one's the best? Personally, I like this one the best. Because I put the matrix in the calculator, it works no matter what. It works whether the system has a unique solution, whether the system has no solution, or whether the system has infinitely many solutions, as long as I know how to read my calculator. These two only work if the system has a unique solution. If you have no solutions or infinitely many solutions, both of those two, matrix algebra and Kramer's, fall apart. And what about this one? Well, it works no matter what, but I don't like to do things by hand. I'd rather use the technology. Right. This brings us to the end of chapter 2, which means you should be able to finish up all the homework, and I think we have an exam covering chapter 2 coming up. Alrighty, have a good day.